Okay.
Do I have to do anything? No.
Just to share your screen. Introduction. So good afternoon, dear colleagues, dear friends. Welcome to our seminar. Today in many countries it's holidays. It's the Monday, but still I'm very satisfied to see many friends in our Zoom room today. It's my great pleasure my great honor to introduce Henry Wolkowicz from the University of Waterloo, Canada. Henry Wolkowicz is one of the leaders of the optimization community in Canada and worldwide. He has a broad profile working on continuous topics, development of algorithms, metrics approximation, cost analysis, but also on discrete topics, optimization, in particular on relaxations of discrete problems. He had very important contributions in the area of interior point algorithms for linear programming, for STP. So he has an impressive list of publications, a very wide profile, and it is our honor to have him as speaker in our seminar today. Today he will talk on a topic which is related to interior point methods, but in a very hot area, the area of quantum algorithms, quantum computing. So Henry, you have 45 minutes for the talk.
Thank you, Radu. And yes, thanks everybody for attending. Yeah, so I changed a couple of the words in the title. And as you can see, this work is with these other 4 people here that I list. And if I run into some difficulty, I think some of my co-authors that are here will help me with some of the things that are in this paper. Okay, so here's the motivation, the outline. So in this area, what's important is to find a lower bound, a provable lower bound for this problem, for this key rate. Okay? And we want to find to be able to find an accurate key rate, we need to minimize a convex programming problem. It's a nonlinear convex problem. So you can see the objective here is the relative entropy. And what's interesting about this function is that it's the trace of a matrix rho times a matrix log, the log of rho, minus another matrix sigma times the log of rho. So this is convex relative entropy. And the matrices are positive semi-definite matrices. And we're going to see one of the things that's currently being current difficulty with this problem is that people are working on instances where, because of the constraints and the structure of the problem, that these matrices are singular. And so taking the log of singular matrices and evaluating this function and derivatives is very difficult. So this is what we'd like to look at. So this problem is an ill-posed problem because it's currently working on the boundary of the semi-definite cone. And so we would like to look at regularization for this problem. So my talk is divided into 2 parts. First, I'd like to look at the theory that's involved in regularization and looking at the upper and lower bounds for this problem using facial reduction. And second, I want to look at developing an interior point method for the problem. And this is in particular something called a Gauss-Newton type of interior point method for the problem. And so currently what people are doing is they're using perturbations to avoid the singularity of the semi-definite matrices. And this is what we would like to avoid, because as we all know in optimization, if you're doing perturbations, then it's very difficult to get accurate solutions. So especially if you're working on an ill-posed problem. Okay, so this is the quantum, the QKD background. So QKD, this is the art of distributing secret keys between two parties. Usually they're called Alice and Bob. And what we'd like to find is this secret key rate, the number of bits that are required to keep the secret key rate secret. Okay? And so this calculation of this secret key rate is at the core of security proof for these QKD protocols. The calculation involves the convex minimization, or particular finding an accurate lower bound. And what's interesting about this problem, and this is sort of based on the Heisenberg uncertainty principle, is that one can tell if somebody's eavesdropping. So if Eve is eavesdropping, this can be detected if we have enough bits in the secret key. So the reason why this is so interesting is that even if a quantum computer is developed, the secret key generated by this remains secure. So here's the problem that we're looking at, and this is following this paper by these three authors. And this is what the problem looks like. This is the relative entropy function. We have a semi-definite constraint over here on density matrices, which means the trace is 1. And we have a linear constraint on the semi-definite matrix. So as I mentioned, this is what the relative entropy function looks like over here. We're working on Hermitian matrices. So these are complex matrices. Okay. And the concrete form for the semi-definite constraint is the inner product, or the trace inner product of taking the trace of the product of two semi-definite matrices. And our constraints, well, our objective function rather, is going to involve these functions, these linear transformations. They're completely positive maps, and they're given in the form of these summations of these matrix products. So this is what they look like. G of rho is a completely positive map given by the sum of these matrix products, sort of a congruence looking like matrix product with this property here that the sum is less or equal to the identity. And this less or equal to is in the Loebner partial order, in the semi-definite partial order. So Radu, if you see a question, please tell me.
Sure.
Okay. So here's the definition again of this completely positive map. It's the summation of these matrix products, okay, and the properties that it has. And the other map is the Z. It's very similar, except it has some extra properties on the matrices involved. And each of them is idempotent and self-adjoint. And so it's an orthogonal projection. And the sum is the identity. And so these are resultants of the identity. Okay, so this map is actually a self-adjoint projection, an orthogonal projection. And it's acting on the space of Hermitian matrices. So here's a little lemma on this linear map Z. If the trace of the semi-definite matrix is less or equal to 1, and the matrix is positive definite, then the trace of delta log Z of delta is actually equal to this symmetric way of looking at it. We can add the Z to the front. So this is a very useful little lemma that simplifies the way that we're going to be looking at our problem. Okay. So again, if we go and we look at these functions, these relative entropy, the functions like the relative entropy function that we're talking about, they have an implicit constraint that that you need to impose so that you have finiteness. And these are constraints on the ranges of these matrices that are involved. And also these functions are jointly convex in both matrices, both matrix arguments. So we can go with a simple substitution for these functions, remove them from the objective and add them as a constraint. And why do we want to do this? Because we want to apply facial reduction. I'll mention what facial reduction is in a minute. Okay. So this is equivalent, completely equivalent to the original problem just by removing these mappings from the objective function and adding them as constraints. So again, just to remind you that our final goal is to find this asymptotic key rate. And to do that, we want to find a reliable lower bound for this problem. So here we have a minimization problem. In some sense, it's a simple semi-definite programming problem. But what's interesting is the objective function is nonlinear. There's linear constraints here, those interesting completely positive constraints. And there's a hidden implicit constraint on the objective because the domain of the objective needs to make the objective finite. So there's implicit constraint on the objective. Okay, so facial reduction, it's something that I worked on with John Borwein when I actually in my first year, even before I had my PhD. So it's quite amazing that this has continued and followed me around for my whole career. And it's quite interesting how useful this has become, this facial reduction. So in convex optimization, we all know how important Slater's condition is, strict feasibility. So in semi-definite programming, this means that you have a strictly feasible point, the matrix, that there exists a matrix which is positive definite that satisfies the linear constraints. So this Slater's condition is sufficient for strong duality, and it's equivalent to numerical stability. If you don't have Slater, then you don't have numerical stability under right-hand side perturbations. Perturbations of the right-hand side of the constraint, so perturbations of gamma. And what's interesting as well is that Slater fails in surprisingly many applications. So many of you know Rademacher's theorem. If you have a locally Lipschitz function, then your function is differentiable almost everywhere. And when we do optimization, we're always working on locally Lipschitz functions. So why worry about functions that are not smooth? However, in optimization, we're always working, not always, but so many times we're working on non-smooth functions, especially objective functions are generically non-smooth. Why? Well, we're pushing things to the boundary, and in optimization, we end up working with non-smooth problems. And the same thing seems to happen for Slater's condition. Many, many models end up having problems where Slater's condition fails. Seems to happen for many, many applications. And I mentioned some of them over here. There's a recent survey that I did with Dima that I reference over here. And I mentioned some of the applications over here. So what are the advantages of facial reduction? We get strict feasibility, we regularize the problem, and at the same time, we end up simplifying the problem. It ends up being a smaller problem. So here's some of the surprising applications are to Euclidean distance matrix and low rank matrix completion. These are very, very difficult problems, and facial reduction dramatically simplifies these problems and allows you to solve them. Okay, so here's some of the preliminaries for facial reduction. So I'm sure in this community, everybody knows what a convex cone is, what the dual cone is, or what the face is. This is just a generalization of a face of the non-negative orthant. And what's interesting is that faces for the semi-definite cone have been understood for many, many years, going back to the 40s. And if we take a point in the relative interior of a convex subset of the semi-definite cone, and we take the spectral decomposition, then the face of the semi-definite, the smallest face of the semi-definite cone containing this matrix here, or this set F, can be written and represented in many ways. And this last line in red is what I would like you to look at. There are two ways to represent faces. One is an inward way, which shows you that every face can be represented with a smaller dimensional cone. And the other is this exposing method, which says take the original semi-definite cone and intersect it with what's called an exposing vector. And this gives you the face as well. So these are two ways, and they're both very, very important and very useful. So how do we do facial reduction? So people have done this, have seen this. This is, I guess, well known in the area. It's really just a Farkas lemma type result, a theorem of the alternative. It says that Slater's condition holds if and only if the following fails. So exactly one of these conditions hold. And what is this condition here? It means that you can find an exposing vector. If you solve this linear system, z is not equal to 0, then you get an exposing vector, and that exposing vector gives you a face of the cone. Okay. So again, here's the definition of the minimal face. If we take a set S, then the smallest face containing that set S is called the minimal face. And it's essentially the intersection of all faces of the cone, which contain S. So I'm just working on the semi-definite cone, but all of this was originally developed with John for general convex cones. Okay, going back to our problem has a linear manifold, linear constraints, and those constraints are defined in this way. Over here, this is using it's trying to exploit the Kronecker structure that's hiding for these problems, for these quantum problems. Okay. And also, this is called the partial trace in quantum computing. This is a well-known transformation in quantum computing. And essentially, it's equivalent to applying these constraints on the matrix rho, where these theta j's are basis matrices in the smaller dimensional space. Now, what we've done is, because of these constraints, if the data given by this matrix rho sub A is singular, then this means that you lose positive definiteness for the original problem. And so you can use a spectral decomposition of this matrix rho A and obtain facial reduction and do this very, very accurately. So this is the first step of facial reduction. We call it partial facial reduction step. And what's important is it's an analytical facial reduction. It can be done very, very accurate because the spectral decomposition of a Hermitian matrix, the condition number for that step is 1. This can be done extremely accurately. So essentially, we really don't have to worry about round-off error for that step. So this is the first step of facial reduction. Okay. So an interesting property, if we do facial reduction, it ends up looking like this. The matrix Y can be represented with this matrix product where R is a smaller matrix. Now, if we have facial reduction, then we've proved this little lemma that the matrix log function, the trace of Y log Y, can be evaluated using this smaller form. Okay. And this is the proof for this little lemma. Now I've added the proof because it sort of emphasizes what goes on for these relative entropy functions, why they're difficult. And they're difficult because you need to evaluate the matrix log on singular matrices. And what do? You use the fact that 0 log 0 is extended to be 0. And why do you do that? Well, if you took x log x and took the limit as x goes to 0, you would get 0. And so this makes sense. Okay. And so this little lemma allows us to evaluate this function on singular matrices. If we can do facial reduction, we can then evaluate it on positive definite matrices. So this is the key about why facial reduction allows us to regularize the problem. So this is our key. The word key comes up too often in this talk. Quantum key. Okay. The other type of, so that was a novel type of facial reduction, which is not done just using the theorem of the alternative. Another novel type of facial reduction is given over here for these completely positive operators. For these completely positive operators, we have another lemma that shows that we can do facial reduction explicitly using a spectral decomposition. The range can be found using the eigenvectors, and so that's found using a spectral decomposition. Condition number is 1. We can do this accurately, and so the facial reduction, which is given in this last line, can be done accurately for this step as well. Okay, so it can be done accurately for the row A, the partial facial reduction that was hiding in the linear constraints, and it can be done accurately for these completely positive operators. So we can do this for the two constraints for those two functions that we had, and we get these linear maps. This is a bit, the details for this are a little bit complicated, several steps, so I cannot include them here. But the key is this is what we get. We end up with a nice positive definite matrix in the objective function, and we end up with these constraints here. And after rotation, we end up with this very, very simple problem. The problem looks just like our original problem, except for this symmetric form that we have here, and the fact that positive definiteness is preserved. So we now have our regularized problem. We have everything looks exactly like our original problem, a linear constraint, except Slater's condition holds for this problem. The objective function, if rho is positive definite, the objective function, the log, is evaluated on a positive definite matrix. G hat and Z hat preserve positive definiteness. Okay, so this function is well defined on the interior of this set. We have interior. We can now look at an interior point method for this nonlinear problem.
But I have a question, Henry.
Yeah.
So you said the objective function is convex in both variables?
Yes.
Okay.
Jointly convex, yes.
I don't see this. I mean,
I know it's not obvious, but
okay.
yeah, this is something which is well known in quantum books, and yeah.
Okay.
Yeah, it's not obvious. You're right.
Okay, thank you.
Yeah, yeah. So here we have two variables, and they're positive definite. So this objective function is jointly convex in both variables.
Okay.
Yeah, and I guess, is there an easy way to see this? I'm not sure. I guess we'd have to write down the Hessian. So the Hessian for this is very non-trivial.
Okay.
To evaluate and talk about the Hessian, you might imagine the Hessian for log, matrix log, is something which is very non-trivial.
Mhm.
So to prove this, you would not find the Hessian, but you would evaluate the Hessian in a direction. So that's what, whoops. So actually, that's what we do here. I have a little bit of a discussion over here. So this is the gradient. The gradient is very easy to find. Easy, well, it's a little bit of a discussion. This is known before, that this is the gradient. And this is, the Hessian is very difficult to talk about. But because of this, you can talk about the Hessian in a direction. So this is the Hessian evaluated in a direction. And you only need first order information to evaluate this Hessian. So if this Hessian is evaluated in a direction, we have to show that the right-hand side inner product with the direction delta rho is greater or equal to 0 for all delta rho. This is how you would prove it. So is this obvious? I'm not sure how obvious this is, but this is how you would prove it.
Okay.
And it's a statement in many books. Yeah, thanks for the question. So this is where I would ask my co-authors, gee, or how, which book, where does this appear? Okay. And in the limit, we get a subdifferential, but now we can talk about a subdifferential because from the inside, everything is positive definite. So we can talk about limits. Okay, part 2. I guess I'm a little bit on time, 25 minutes, right?
So we have an answer in the chat.
Oh,
yeah.
okay. Thank you. Can you read the answer?
So the objective function is called the quantum relative entropy function, and the proof of its joint convexity property can be found in the book The Theory of Quantum Information by John Waitrose. Yeah.
Okay, and that book is online.
Okay.
John Waitrose is at University of Waterloo.
Okay. So thank you.
Okay, ask him what page number.
Yeah, he wrote the page number, page 276. Okay. Yeah, so very precise. Yeah.
Okay, thank you.
Thank you.
Okay.
This is your co-author, Hao Hu.
Oh, okay. Thank you. Thanks, Hao. Okay, part 2. So part 2, we have this problem now, which is regularized. Strict feasibility holds. And the objective function is well defined for all positive definite rho. It's convex. Okay. What do I want to do now? I want to look at duality and optimality conditions for this nonlinear SDP. And I want to derive something called a Gauss-Newton search direction. And I will motivate why I'm doing something called Gauss-Newton, which is different than the literature. I've worked on Gauss-Newton before with some people, and so there are papers about this. But I will motivate why Gauss-Newton is useful and why, especially for this problem. And also, there's some interesting things that will happen by using Gauss-Newton. We can actually get exact primal feasibility in the algorithm. So what does exact mean? So everybody knows, maybe not everybody, but most people know that Newton's method is fantastic. And it's fantastic as well in the fact that if you ever take a Newton step, length 1, often called the Newton step, then every linear constraint is perfectly feasible. So everybody in SDP likes to take a Newton step because then all the linear constraints become perfectly feasible. They're very, very happy, right? However, and then you can also prove that steps after, even if they're not length 1, they stay perfectly feasible. This is fantastic. However, this is theoretical. If you take a step length of 1, you get perfect feasibility. However, if you take a step length of 1/2 next time, theoretically you get perfect feasibility, but there's round off. And then the third iteration, the round off, gets amplified. Every iteration, the round off is amplified, and you lose perfect feasibility. And this is why this perfect feasibility is often corrected in interior point methods. However, we're going to do something because of this Gauss-Newton method, which allows us to maintain exact perfect feasibility, primal feasibility at every step. And we will be able to do something similar for dual feasibility, which will allow us to get lower bounds. Okay, so, so in the optimization community, we all know Lagrange multipliers, which probably not everybody knows is really due to Euler, Lagrange supervisor, but anyway. We use Lagrange multipliers. This is Lagrangian. For the problem, we add Lagrange multipliers y. Strong duality is that the primal is equal to the dual, defined over here. So I'm taking the row positive semi-definite constraint and adding it to the Lagrangian with the Lagrange multiplier z, which is a semi-definite matrix here. And strong duality, this is again something which has gotten lost in the literature, means that D star is attained, which is very important for stability. So there is a y and a z where D star is attained. And this is the optimality conditions. So the beautiful framework that developed in the middle 80s, this primal dual framework that developed interior point methods, beautiful dual feasibility, primal feasibility, and complementary slackness. And now all you have to do is apply Newton's method to these optimality conditions. Of course, this inner product is usually written as a product to be able to apply Newton's method. However, in SDP, we cannot apply Newton's method because rho z is not symmetric. So we lose the square system, which adds some very interesting subtlety to semi-definite programming. So the first thing we do is we're going to change primal feasibility. We're changing primal feasibility by using a null space representation. How do we do that? Well, we just find the null space for the linear map. We call it n star. The range of n star gives us our null space. And so you can see over here, this line is the null space representation for the primal linear manifold for some v. And so now, what do we do for interior point methods? We derive the perturbed optimality conditions. I'm not going to derive them here, but you usually derive them using a log barrier. Okay, and the log barrier results in the barrier parameter mu. Okay, so this is the usual way. So this is very familiar to people, except for the middle equation. The middle equation is a funny looking primal feasibility equation. It's given by this null space representation. Okay. Now here is what I was saying before. Exact primal dual feasibility. This is what's nice about the null space representation. If I go and find a search direction given by delta rho, delta y, delta z, and delta v, then I update rho using this equation over here, then I get exact feasibility. I get exact primal feasibility. The only reason I could not do that is if rho was not positive definite. But if I could do it with positive definite, I get exact primal feasibility, and it is maintained throughout the algorithm. The only round-off error comes about by the calculation of n star, the representation of the null space. So that would be the only place where round-off could come in. And the other thing is the dual feasibility is the same thing. If I have delta rho and delta y, I could update delta z, I get exact dual feasibility. This is going to be important for the lower bound. We're going to see why. The trouble, again, is that delta F here is nonlinear. So Newton's method only preserves exact feasibility for linear. So exact feasibility for the dual will not be maintained. And so this will have to be updated. This won't be, we won't be as happy there. Okay. So what is the next thing for methods? Newton's method, we need linearization. Gauss-Newton, we need linearization. This is the linearization, but as I emphasize here, it's overdetermined. We cannot apply Newton. So this is the interesting thing about our area. Everybody has applied Newton's method to SDP, but if you ask somebody in numerical analysis, I have an overdetermined system, what should I do? Nobody will say Newton's method. Everybody will say Gauss-Newton. This is numerical analysis. This is what the numerical analysis community would say. So here we're going to do Gauss-Newton. And we're doing it for several reasons. One is because that's what numerical analysis would do. But the other is that people who apply Newton's method, the back solve ends up bringing in some catastrophic round-off error. This is what's hiding in semi-definite algorithms. And this is why all the SDP codes that you look at now have a terrible time getting high accuracy. They're very, very susceptible to round-off error. And if you give them ill-posed problems, they will die very, very quickly. The best codes, I won't mention the best codes because I'll get sued, right? But anyway.
Yes. Very good.
Yeah. The way car marker was sued the way OB1 was sued by car marker. But anyway. So what do? We're going to do find the search direction. We do the first elimination for delta Z, and then the second elimination for delta rho. Okay. And we end up with this system. What I think, I'm not sure about my co-authors, but what I like about this system, being a mathematician, is it looks very complicated. It's so hard to believe that we solved this system, right?
Indeed.
It's the Hessian. The Hessian is acting on a Hermitian matrix. And this Hermitian matrix is obtained by the null space operator acting on another Hermitian matrix. It's a really complicated system, but we solved it very accurately. Okay, so here's the algorithm. The quick loop, this is the standard interior point you have. You find the search direction, you update the row, delta rho, delta Z, you choose a step length, and then you update your barrier parameter. And I haven't included the lower bound and the upper bound here. I'll discuss this below. This is a standard interior point approach. The only difference is here, right? Because this is the Gauss-Newton elimination that gave us that. So what's hiding is we're finding a least square solution of an overdetermined system. We're not solving a Newton direction. But step length 1 works for Gauss-Newton, just like for Newton. So you can prove that. The step length 1 theorem. Okay, this is some of the implementation. We made sure that our null space representation was found in a stable way and did not lose sparsity. So if our original problem had sparsity, we did this in a very special way so we would not lose sparsity, and we tried to maintain a nice triangular structure. We also did preconditioning. We used optimal diagonal preconditioning. So this is the MATLAB line that we used for the search direction. RHS is the right-hand side, the complicated right-hand side you saw up there in the equation. This is the Jacobian that you saw in the equation. And the D is the preconditioning that we do. So this single line in MATLAB gives us our preconditioning and solves for our search direction. Okay, and it performed remarkably well. It was very interesting how well the ill conditioning was improved by by the diagonal preconditioner. It was really interesting. Like we had preconditioning of the order of 10 to the 36, and it went all the way down to like 10 to the 8. It was really quite interesting. Okay. The other thing that we did is how do we find an upper bound? If we didn't have a primal feasible exact solution, we found the nearest primal feasible by doing a projection. But as we mentioned, as soon as we got exact primal feasibility, forever after, we maintained exact primal feasibility. This happened very early in our code. So every iteration, we got a better and better and better upper bound. The lower bound, this was interesting. So this is one of the other things that in the literature comes up a lot. People solve an SDP and say, they take a discrete hard problem, they take an SDP relaxation, they solve it and they say, I have a lower bound to my SDP. However, what they ignore is that their SDP is solved only approximately. And so their result is not a lower bound, right? However, you can use weak duality. And then weak duality gives you a true lower bound. So the dual of the SDP gives you a lower bound, but the primal does not, because you cannot solve the primal exactly. So weak duality is something that is really good, but for weak duality, you need a feasible dual. You need a dual. So this is what we did. We used this form where I remind you that we had Z explicitly given this way. If you write Z this way, this gives you perfect weak duality. And if you're able to do that, then you just evaluate this lower bound. And the proof is trivial here, because we have a dual problem given over here. So we just need any Y and any Z semi-definite. Doesn't matter what it is. As long as it's semi-definite, we just plug it in. The hard part is that we have to choose Z to make sure that the row is the minimum. And this is stationarity for the inner function in the min. Any questions? No questions, eh? Okay. Okay, so I think I've managed to get through. So this is, I think, interesting for this lower bound. This comes up a lot, trying to find a valid lower bound for these hard problems. And for this problem especially, the important thing is to get a valid lower bound. Okay, numerics, and then I'm done. So here are some problems, and we're comparing with that paper that I mentioned to you, which employed a Frank Wolf algorithm. And what's interesting is this is their Frank Wolf algorithm over here. This is Frank Wolf with this new facial reduction. And you can see the facial reduction regularizes their problem.
Who did it? Can you say it again? Who did it? Who applied Frank Wolf to the same problem?
Oh, that's the paper, the three authors paper that I mentioned on the third slide.
Okay.
I have an advantage here.
Yeah.
Whoops, what did I do? I have an advantage because I have the screen. It's these three authors here.
Okay. So are they physicists?
Yes.
Okay.
So Norbert, the middle author, Lutkenhaus, he's the person that we worked with, and he's one of the co-authors on our paper. I do not know the other two. Like one of our co-authors, Jay, who's in the audience here, maybe he can say more.
Okay.
But I think all three are physicists, yes.
Thank you.
Lutkenhaus, definitely. So they applied Frank Wolf, and they used perturbation to be able to apply the objective, to evaluate the objective function. And so these are the results without facial reduction. This is CVX quad, which is a code available in MATLAB to solve these relative entropy problems. and they improved on CVX quad. But you can see facial reduction improves what they did. And this is what our code is. Our code is essentially, time-wise, it just flies. If we have time, I could show you how code runs, how fast. But 0.2 seconds is fast, right? And this is the accuracy. And the reason it's 13 decimals is we didn't ask for more, right? But it's hard to get more on a computer. So Gauss-Newton performed really well. And we stopped here because this is all that CVX quad could handle. Here are some more problems. So we got rid of CVX quad here because it couldn't handle these problems. Again, Frank Wolf with facial reduction did better. So we were very happy that this facial reduction showed that it could help the Frank Wolf. And this is the Gauss-Newton. And I just want to mention that if you just did a regular primal dual interior point here, you would not be able to get this accuracy. The Gauss-Newton avoids, and I'm not sure if you remember the backsolve steps, but the backsolve steps are accurate. If you do a regular interior point method, the backsolve steps are not accurate. They inject, and this is even in linear programming, a severe round-off error. And it's very hard, theoretically, it's very hard to get past 8 decimals, square root machine epsilon. And finally, just to show you what that accuracy means, the dots here are the lower bounds from the Gauss-Newton, and the curves for these problems are the analytical results. And so the dots are exactly on the curve. So our numerical results are exactly on the theoretical results, and it really shows relative to the empirical evidence that we had. Okay, conclusion. And I think I am in time.
Yes.
So what we did here is we took off on that paper, and the paper by the physicists who were working on this problem, and we're developing a lower bound with a very similar philosophy in that they tried to solve things with an SDP and then used the duality to try to find a lower bound. So what our contribution was is to regularize this problem and to show that we could do this accurately, and that facial reduction really helps, and that we injected 2 new types of facial reduction. Both of them involve spectral decomposition, so both are very accurate. And they show that you can regularize this problem and make the objective function have a domain on positive definite matrices. And so everything is well defined. And we also have our lower bound is modified so that we have a theoretically proven both upper and lower bounds. And we never had an instance where our lower bound was higher than our upper bound. And so the theory really coincided with our empirics. And we also used the Gauss-Newton. And I think this shows that the Gauss-Newton approach, especially for this problem, which really is very, very ill-conditioned, even after the regularization. Because what's the domain? The domain is positive definite matrices. We're working on positive definite matrices. The solution is usually a positive semi-definite matrix. It's on the boundary of the domain. The objective function is not defined outside positive semi-definite matrices. So just imagine you're working on a problem. Your domain is a set. And everything outside this set, your function is plus infinity. What do? The tiniest perturbation, you're in big trouble, right? You really, and so you're getting closer and closer to the boundary. and you have to evaluate things accurately. You have to have something which is very, very robust. If you had round-off error that loses positive definiteness, you're dead. So this is why the Gauss-Newton really worked well here. Okay, I'm going to stop there. The references that I mentioned will be in the slides. And thank you if you have any questions. Radu.
Thank you very much, Henry, for a very nice talk, emphasizing the role optimization plays and can play in future in the area of quantum computing. So a very nice talk and nice results. Thank you very much. Are there questions? Yes, Bruno Lorenzo.
Let me see if I can see his.
No, I get it. He will turn on.
Oh, he will talk to me. Okay.
Oh,
hello, Bruno.
Oh, hello.
Good to see you.
Thank you very much for the very nice talk. And one thing I'm a bit curious is about the properties of the dual problem, because you've regularized the primal problem as to have Zeta's condition. I'm just curious of what happens to the dual side in terms of constraint qualifications. That is one thing. And the other thing is whether the primal problem is always attained, for example.
Yes, the primal problem is always attained because of the fact that we have, these are density matrices. The matrices are density matrices. Now, I don't know if you remember here. So the feasible set is compact.
Okay.
Okay. So the primal is always attained. The dual, of course, strong duality holds because of the regularization. Now, your question about is the dual a regular problem? That's a very good question. And it's something to tell you the truth, I did not think about.
Because I'm asking this because there are some ill-behaved problems. Ill-behaved in the sense that if you try to feed it to a STP solver, you might not get a correct answer. And partly, and some of them, they satisfy latest condition, but just at one side of the problem. So you don't have latest condition at both sides. But from your numerical results, it doesn't seem to be
well, yes and no. So what the numerical evidence show us is that the Jacobian, because when you run the code, if you run the code, we output so this is a typical run. Okay, I'm going to show off here just to show you how fast this is. Now it's not going to be fast. Oh, this is one of the slower problems. Okay, but that's fairly fast. This is one of the hard problems. But you can see over here the condition number of the Jacobian.
Oh.
So we actually keep track of the condition number of the Jacobian, and it grows very quickly. So this problem, even after regularization, is ill-conditioned. And I think your point is very well taken. I am not sure that the dual satisfies Slater. But the ill-conditioning of the Jacobian indicates that, first of all, there may be it indicates one of two things. Either primal or dual is not unique, or the dual does not satisfy Slater.
Oh, I see.
So I'm not sure. I have not thought about it enough.
Okay.
But what's happening in this code, just for your interest, is that the red just shows you each time that the lower bound and the upper bound are being updated by exact feasibility. The 0 here shows you that exact feasibility is maintained at each iteration. So that confirms what I was saying. Sorry.
So for the sorry. So for this instance you were just solving, what were the size of the matrices? This large one.
So the sizes of these matrices. So
144 by 144.
oh, that's after being decreased from facial reduction. Yeah. Yeah, so it's 144 and then they get decreased.
Mhm.
So originally they're 144. But there's a lot of constraints that are hiding.
I see. Thank you very much.
Thank you.
Yeah.
So we have a further question, Misha Kochvara.
Yeah, hello, Henry.
Hi.
I have a question about the diagonal preconditioner you mentioned. So that was
Okay.
for the linear system, right?
No, for finding the least square solution. So here is the overdetermined least squares.
Okay.
And what we do is, yeah, so the Jacobian is the left-hand side. And the variables are the delta V and the delta Y. And this is the right-hand side. And so we're using MATLAB's backslash, which is a least square solver, to solve this. And the preconditioner is a right-hand side preconditioner for the Jacobian. So it's a column preconditioner.
Okay. And
So,
okay, so
yeah.
that was my question. You are still using backslash solver. Okay. Yeah.
Yeah, there's the backslash. Okay, so this diag here preconditions the Jacobian.
Mm-hmm.
Then we backslash into the right-hand side. And then we unprecondition the result.
All right. Yeah, I see. Yeah. And D is, yeah, I see it here. Yes.
Yeah, little d is just a vector.
Mm-hmm.
It's a vector obtained from the columns of the Jacobian, the norm of the columns. So I don't know if you know this little paper. This is a paper by John Dennis and myself. We proved that this is the optimal preconditioner, the optimal column the optimal diagonal column preconditioner for what's called the omega condition number.
Okay. Yeah. All right. Thank you. Thanks.
Thank you. Are there further questions? So I have a question. Actually, I have two questions, Henry. So, so you had this little lemma, which allowed you to reformulate the objective function, but there was one condition there, namely that the trace of the matrix is less or equal than 1. And then this trace condition was not anymore available. This was my impression later on.
Oh, no, the trace condition is hiding.
Okay.
Yeah, the trace condition is hiding in the gamma.
Good. Okay.
Yeah, it never disappeared.
Okay. So even later you had it even when you, like, let's say, consider dual and everything.
It's hiding, yeah.
Okay.
What's interesting by facial reduction is that many of the constraints become redundant.
Mm-hmm.
So if you think about linear programming, and suppose you have a linear program and many of the variables are 0 identically on your entire feasible set. So that means your feasible set is really stuck to a face of the non-negative orthant.
Mm-hmm.
Okay, and you have a lot of constraints. And now you do facial reduction, which means you throw yourself into this smaller face. And you throw away the variables that were identically 0 because you don't need them anymore. So you have many fewer variables. Now, just imagine if this was done a lot, and you had 100 constraints and 1,000 variables. And let's suppose that you were really successful and you threw away 950 of the variables. You only had 50 variables left, which means you have 50 variables and 100 constraints. That means you've made at least 50 of those variables are redundant, right?
Yeah.
So that sort of really emphasizes what happens. In general, many of the constraints by facial reduction become redundant and get thrown away. So the problem becomes becomes smaller, both with constraints as well as variables.
Yeah.
But the fact that the trace is one is hiding.
Okay. I have a second question. I talk about facial reduction. So can you show again this characterization you had? There was a result.
The theorem of the alternative.
No, there was a characterization by using an element relative interior of the face.
Oh, yes.
Okay.
This here.
Yes. So you take an x in the relative interior of f for which you have this decomposition.
Orthogonal eigenvalue decomposition.
Okay, and then you can write f by using p and okay, but then what about for another x? So is
Okay,
this
so yeah, so this is interesting about the faces, and
Okay.
this is part of this is 2. 2 says that every x in the relative interior has
Okay.
the same range,
very good. Okay.
and every x in the relative interior has the same null space.
Yeah, very good. Okay.
And then you can talk about the boundary.
Yes. Okay. Thank you. Great.
Thank you.
So then let us stop here. Thank you very much, Henry, for a nice talk, for a nice discussion, very nice results.
Thanks. Nice to see Mikai and Bruno and Mazir.
And also many other friends. So I want to thank participants for being with us today. This is a day which is holiday in many countries. And yeah, thank you for attending this very nice talk. So we will post the video and the slides on our website. Just want to announce that the next Monday, our speaker will be Michael Ulbrich from TU Munich. So thank you, Henry.
Yeah, I hope to see everybody face to face soon.
Yes.
So thank you, Henry. We did enjoy. Thank you, Radu.
See
Thank you
face
for
to
the
face.
talk.
Bye.
Thanks, Henry. Ciao.
Thank you.
Veronica, hi.
Good to hear you.
Nice to see you. Nice to see your name, Veronica.
You're right. I didn't show my face.
Nice to hear your voice. Same laugh.
Yeah.
So Henry, one more question.
Oh,
So do you want to publish the paper in a math journal or in a physics journal?
we're going to publish in a quantum journal.
Very good.
We're going to listen to our co-authors.
Yes. Yeah, this is great. This is great. This is great. Okay. Yes. I mean. Okay. So thank you very much.
And also, I guess I can advertise that our co-authors, they have a system at Waterloo, so they're hopefully going to, so their Frank Wolf solver is part of their system to calculate this QKD, and hopefully, and they're hoping to substitute this solver in place. So,
Yes.
so if you need your QKD solved, you know where to go.
Yes.
And in quantum journals, is the speed of handling papers are quantum. So
and Mark, and the impact factor is much higher, I guess.
Impact factor is quantum.
It's quantum, yes.
whatever it means.
Yes, of course, I agree. Yeah, but
Nice
Thanks,
to see
Henry.
you, Mark.
Yeah, thanks, Henry. That was interesting. You know that I like entropy. So
Yes, I know that. Yes, I know that well. Yeah.
Because entropy goes with chaos. So that's why.
I know that
Right.
back all the way from Halifax. Yeah.
Yeah, that's correct.
How are you,
Okay.
Mark? How are you, Mark? How is life?
So far so good. We are doing well.
Yes.
Hopefully it will last. We'll see.
Yes.
So Mark, I got my vaccination.
Oh,
Gail,
congratulations. Congratulations. That's good. Well, is that in Canada? You are what? You have been eligible because of your age or what?
because of my age, yeah.
I see. Okay, so
But they've lowered the age dramatically.
okay. How many? What is the percentage of people vaccinated now?
Oh, it's still like 13%, I think.
It's not too bad for. How about you, Radu?
15.
No,
15.
15?
Yes.
So you are doing very well in Europe. You are a leader.
But yeah, of course, I agree. Yes.
No, really, I'm not
Just
joking.
Austria. I mean, for us, it's I guess 6 or 7, or and Germany is 10, I guess. Yeah.
Uh-huh.
No. So
Well,
Austria is 15. Yes.
yeah.
15, not 50. 15. Yes.
Oh, that's good.
But Mark, I hear that from what I read, that the infection rate in Israel has really dropped. So the vaccine works.
Yes, that's why I told to Radu so far so good. Yeah, it works very well so far. Yeah. But we are approaching, essentially, we have vaccinated all the population except the young population. Israel is a young country, so we have something like more than 35% people which are below the age of 16 and we cannot get vaccinated because there are no vaccines so far. So
It will be. I mean, Pfizer announced some. Yeah.
yeah, probably in July, not before.
Yeah. But we are all looking to Israel, and we are. Yeah. Look, this gives us hope. Yeah.
Yeah, we no. Otherwise, that's over 60, 62 or 65% of the population, which is
Okay. Yeah.
be vaccinated. So that's yeah, it works quite well.
Okay.
We'll see. You know,
What about restaurants? Are they open?
everything is open now. Even we
Very
open also the campuses for. I mean,
Very good. Very good.
not all the courses, but most of them. And I mean, participation is only according to the special health protocol.
Mhm.
Meaning that you still have to keep distances and so on and so forth. And of course, students have to be vaccinated to enter in class, otherwise they cannot enter in class.
Okay.
So they have to go to a Zoom lecture. So it's a hybrid way for the students. So for the students, it's a major improvement. Yeah, everything is open this year. I mean,
But they prefer to go to the university, I guess, no, or to stay home?
yeah, well, especially yeah, it has been a tough year. Okay, especially for first undergrad student because they didn't have the experience of what it means to be a student.
Yes, indeed.
So essentially for them, I think that the rules are. I'm not very much involved because I'm not teaching anyway. I'm not teaching this semester, but I'm not teaching undergrad. So, but I think that it's. I think that for them, almost all the lectures are in class now. Yeah.
Oh, very good.
Yeah, since this week. I mean, last week because it was Passover holidays in Israel until yesterday, essentially. So.
Okay.
So Ontario is the reverse. We've locked down again for a month.
Where? In Ontario?
Ontario.
Oh, yeah.
Yeah.
Yeah, well, apparently this is the only, the only way of getting out of this pandemic is with the vaccine, hopefully. I mean, we'll see. Because otherwise, I mean, things are not working anymore. Even locking down is not very, I mean, perhaps because probably people are getting tired of that and they're not respecting the rules, okay? So, which makes sense also.
Yes.
So anyway, yeah. So we have open theaters, cinemas. Everything is open now. Restaurants, pubs, whatever.
This is great, and yeah, I mean,
yeah. They are even planning maybe to allow people to drop the mask outside, not inside.
Okay.
Maybe I don't know. That's one of the recommendations of some of the medical Ministry of Health people. They think that outside it's it should be okay now. Since there is essentially the effect of self-immunization thanks to the massive vaccination.
Yes.
So yeah, well, we should say thank you to our prime minister, even though he's in big trouble. But he was a very smart guy. Actually, he was the smartest.
I wanted to ask you, what about the new government? Do you have a new government? Not yet.
No, we don't have a government. No, it's a deadlock. So, but we are used to that. It's not new.
Oh, no.
When's the next election?
Well, this is actually an infinite process that will be. If it doesn't work now, probably will be in the summer sometime.
Well, Israel will be proof that countries work better without government.
That's, well, in Israel, it makes sense in some sense, because I mean, essentially what people, I mean, the country is working because there are some serious people here that are doing their job, and it doesn't matter with, as you said, if there is a government or not. But even, well, I would say, for example, in Europe, I would say that some of the government are causing a lot of damages to their own country. So
yes, this is correct. Yes, there are many examples.
Yeah, so maybe that's a new way of governing a country without a government.
Yes.
I mean, we don't have a government actually for the last 2 years, because it was always a, you know, it
electoral campaign. Yeah.
Yeah, so the part-time government, you know, it's lasted every time. I mean, for the last 2 years we had.
Yes.
Well, our electoral system is a total disaster. So.
Mark, this is Boris. Mark, you know, I have a question, not mathematical question. Hi. What about chance of Bibi to lead this new government? What do you think?
Very difficult question.
For the moment, chances are zero.
Well, you think zero, right?
Zero, yes. 0.0.0.
It means Lapid will come? Yes?
No, I don't think so. His also chances are close to zero. If not zero.
But who has more than zero?
Nobody.
Everyone. No, this is a limit. This is a limit process. Everyone is close to 60, but never approached it. I mean, it's like, you know, it's like the escargot, you know, which is traveling a fixed distance and doing every day, half a day, and so on. So,
but somebody should, you know, should lead the government anyway.
Who should lead the government?
Okay.
I didn't hear. What?
No, he said that you will need a prime minister at some point. I mean,
No, somebody, you know, the country needs a prime minister with more than zero.
Well, for the moment, by the way, if we have a transitional government, as Netanyahu is the prime minister of Israel. The proof is that he was able to do what he did, which was quite a smart move, I would say, to put Israel with being able to vaccinate all this population ahead of time.
But the population was kind of not recognizing this effort. I mean,
well, yes and no, but it's, you know, it's not. It's more complicated than that.
Yeah, of course. But,
Nika, you predict who will be new prime minister? Mark, with your experience, your prediction, who will be new prime minister?
My prediction is that I am very sorry for Netanyahu, because I consider him as a very smart person, and he has demonstrated it again. That's not the first time that he has done a very smart move. And I'm very sorry for him that he's insisting on wishing to stay on power. While he could have other alternatives. For example, he could be nominated or elected as the president of the state of Israel. You know, the president in Israel has no functional or political role. I mean, it's just a symbolic job, but it's a very important symbolic job. And in particular for a guy like Netanyahu, who has an excellent way of, I mean, he communicates brilliantly with all the leaders of the world. He's a very smart guy. He knows almost all the key people on this planet. So being a president could be a perfect for him.
But you do have a president, you know.
Yeah, you know, but the president is ending his term now this year.
I see.
We need to nominate. This is the president is nominated by the Knesset,
Yeah.
and so we need to nominate a new president. So this is perfect for him.
But Mark, actually, the question, I mean, the real question is not what about Netanyahu. What about this so divided society in Israel?
I don't think that this is well. You are probably nourished by some of the press. I mean,
But you have so many people.
I don't think
there is nothing new about that.
I don't think it's so divided. It's not
Yeah,
like
it's not that
it's not
so
like
divided.
50-50 in the US. If you take a
Exactly,
look,
exactly, right.
it's just
that's very
Lapid.
different.
Lapid
The
is taking
division in Israel. Okay, the division in Israel is like when people over the world have tried to understand how comes that Israel has become a powerful nation is in high tech and the startup nation, the so-called. Because if you put 3 Israelis in the same room, I mean, you will get at least 6 ideas and decisions. Or if you hire a new computer scientist in a high-tech company, then the first question of the guy would be, why this guy is my boss?
No, it's very Jewish, Mark. This is very Jewish.
Mark, these are
But what do you want? I mean, this is Israel.
no, but Mark, this is very difficult to form a government. I mean, everything is good.
But that's exactly why, because we have an electoral system which is completely ridiculous, okay,
Yes.
and which is exactly because of that. Because if you put 3 people in a room, you will get 25 different viewpoints. So the business of division is a bit exaggerated, or mostly exaggerated by the press in Israel, because most of the media in Israel is anti-PP for good reason or bad reason, I don't know. I mean, from my standpoint, I think that he should go, but I think that he has done fantastic things for this country. That's why I would prefer him to go now.
If you look at left and right in Israel in terms of, I mean, the left is what, 20%? So the division is very strange. The division is more just people not wanting to talk to each other, but in terms, it's not like.
Yeah, but again, I mean, Henry, again, I mean, talking about left and right in Israel is also because there is no left and no right. No, really, I mean, it's
good lesson to you.
I think, Mark, the people are laughing because we're already disagreeing.
Yeah, that's true.
You know, what happens when too many Jews, you know?
Yeah, well,
Okay. So
that's just an example to prove what I'm saying. Anyway.
So
that's fine.
Okay, guys.
have a nice week.
Nice talking to you.
Bye-bye.
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 Bye.